All right. So, hi, thank you for being here. My name is Julie. I am a blockchain security engineer with Chain Security. Very quickly, I have the pleasure to work with some of these amazing clients to make blockchains more secure for everyone. But today, I'm not going to talk about something that has to do with that. Instead, I'm going to talk about a project that I did at EPFL. You can see the nice campus that we have. It was during my thesis and also during Balelec. We're not sponsored, by the way. But I did this project with Brian Ford from the Decentralized and Distributed Systems Laboratory, which was called Optimizing Commit and Review for Smart Contracts. And as you might have guessed, this is going to be the subject today. Before I begin, I would like to issue a challenge to all of you. As you've noticed, we don't get a lot of questions in this conference, I think. So give me your tough questions, okay? I did this for 6 months, so I'm ready for it. So I'd like to start by asking, what is commit and reveal? And so commit and reveal is essentially the digital equivalent of an envelope. If you see, this is a voting envelope. And next week, I will put my ballot in the envelope and seal the envelope and give it to the ballot point. And why am I doing this? Well, I want both to hide my vote, and I also want other people to be able to take my vote and move it around and also be able to open it at the end of the election. Now, if we want to do the same thing in the digital space, we can use a commit and reveal scheme or a commitment scheme. So we would have the ability to generate a commitment for an arbitrary message, and later we will have the ability to reveal what the message was and give proof that this was actually the original message. Now that means there are two properties we want. We want commitments to be hiding, meaning that they don't reveal anything about the message, and we want them to be binding, meaning that you cannot change your mind or your vote in the middle of everything. Now, how do smart contracts today use commit and reveal schemes? I will give you 3 examples. The first one is ENS. If you've ever registered an ENS name, you saw this screen, which it has you do one transaction, then wait 60 seconds and do a second transaction. And the reason it does that is because the first transaction is making a commitment and putting it on chain, and the second transaction is opening a commitment that was already on chain. And the reason they do this is that if you did this in one transaction, you would be revealing your name in what's called the mempool, which is where the unconfirmed transactions go, and someone could sweep your name in front of you, which we want to avoid. So more generally, we can say that ENS uses commit and reveal to protect against front running. Now my second example is again ENS. At the very beginning of ENS, all the names went up at once, so they made a big sealed bid auctions. And to implement the sealed bids, they did also a commit and reveal protocol. So there was a first phase where everyone went to publish commitments, and then a second phase where everyone went to reveal their commitments and the bids that were inside them. This using both the hiding property, meaning that people cannot see your bid, and also the binding property, meaning that you cannot change your bid after you've seen other people's bids. Now, the third example is an idea that has been in blockchain for a while, which is to generate a random number, which is usually hard on blockchains, by having multiple parties commit to their own random number, and then in a second phase, having everyone reveal their number and mixing everyone's entropy together to get a fresh random number that should be unbiasable and unpredictable. And we'll come back to that. Let's also note that the proof-of-stake algorithm for Ethereum uses a very similar system, slightly more optimized, but with a lot of the same properties. Now, if we look at all these examples, at the lab, we saw a bunch of limitations, namely the fact that you have to do 2 rounds. You have to commit and then reveal. This means that the smart contracts can get more complex because you have to track commitments and things like that. And especially, it's difficult for these kinds of protocols to deal with unrevealed inputs. To expand on that, because only the sender can open a traditional commitment, what if they don't reveal, where you don't want to wait for them? But if you ignore them, this also opens more attack surface. So what some protocols can do is require collateral so that they can take collateral from people who don't reveal their commitments. But then the question is this enough collateral? The other question is, can other people DOS your internet connection so that you cannot reveal? And there's also this problem, which is also in the proof of stake of Ethereum, that the last person that reveals their commitment can look at everyone's commitment and ask again, is this advantageous to me to reveal my commitment now or not? So we said at the lab, there must be a better way. And so what we've been building for, I think, the last year or so is a new architectures for blockchain, where we say, okay, every transaction you can opt into temporarily encrypting your transaction, and there's a threshold network which is able to decrypt them. They have the policy that they only decrypt finalized transactions so that they are already set in the blockchain and they cannot be removed or reorganized. Now this has the consequence that we need to delay the execution of these transactions until they are decrypted, which on Ethereum, for example, could be up to 12 minutes, but we'll come back to that later. So as a note, we're building a prototype. We are not saying it should be a roll-up or it should be 4 standalone chains. We're also not saying it should be EVM, even though the prototype is EVM, but we try to be relatively agnostic with regards to that. Benefits of this approach is, first of all, you get complete front-running protection. You can also argue that you have better credible neutrality because now block proposers will only look at ciphertext, so they can't discriminate against people's transactions. And the last thing is we can implement efficient and safe sealed bid auctions, and I will show you how. So you implement open bid auctions like you would normally. Then you change the length of the auction to be less than the execution delay on the blockchain, and you deploy on a temporary encryption blockchain. And that's all you need to do. You have sealed bid auctions just like that. And we did this in the prototype, which you can see later. Now the question when you do these types of modification is, what about the gas? You know, if you make nodes that follow the blockchain do computation, you have to be charged for that computation. So luckily, the biggest point in our encryption scheme is elliptic curve pairings, and we can align with the policy of EIP 1108, which in the end means that every transaction has an extra 192,000 additional gas for the encryption process. Now, is this a lot? Well, if you go to the Etherscan gas tracker, you will see that they have the figure that a typical swap would cost 356,000 gas. So that means that we use 53% more gas. Now, knowing that you can lose thousands of dollars to sandwich attack, I think in this use case, a lot of people will be very happy to pay this type of fee. The other question that we have is, what about data availability? Well, first off, we can store decrypted transaction after they've been executed in plain text, which means that we can still compress them like we do today. But there's some extra additional data to prove the encryption, which goes down to 144 bytes. Now the question is this similar to the comparing apples to apples? If you were to instead post commitments and then open them, would you have a similar footprint? Depends how you measure because you have to do transactions. But generally, it's in the same ballpark. It's not, one is much more expensive than the other, so I argue that it's comparable. Now, a last feature that we have is, I don't know if you've heard of DRAND. DRAND is also a threshold network which has as a primary goal to generate random beacons regularly. And we use very similar cryptography to DRAND, which has this interesting property that our decryption keys are also random beacons. And in the same way, DRAND's random beacons can also be used as decryption keys, which is why they have also the time lock encryption application that is running today. So this means that if we give access to the decryption keys to the smart contracts, we now have a synchronous source of randomness, which not a lot of blockchains can do this. You know, typically you have to do a call and then get a call back with the fresh randomness from the VRF provider. Now, of course, there are drawbacks to this approach. It clearly requires a hard fork, especially in the case of Ethereum. It also means that EIP 1559 needs to be redesigned a bit because transaction takes some time to be executed. And it's also difficult to say we refund unused gas, because if you do that, you open yourself to a griefing attack where people reserve a lot of gas, but then they don't use it. And then you have a problem with the validators not being paid. We also rely on the threshold network to stay available, which is something that the Ethereum L1 doesn't like, which is why they went with the commit and reveal approach instead. And we will lose most of the benefits of MEV. To expand on that quickly, there are also benefits to MEV and the fact that proposers extract MEV. Namely, they can liquidate very efficiently in lending protocols. They can also do arbitrage, both between dexes and between sexes and dexes. And it leads to less failed transactions. Before Flashbots existed, we had a lot more failed transaction and wasted block space on failed transactions because people could not use Flashbots Protect to prevent their transactions from reverting. So that's also something that needs to be addressed when developing these types of services in the future. A word on that, we are not the first ones to work on this. There are non-academic and academic teams working on these types of systems like Shutter and Favero, and it's always very interesting to keep up with what's going on in this space, so I just want to highlight this fact. Before I conclude, I want to thank publicly a few people, Professor Brian Ford from PFL, Yolande Romeyer from Rendezvous, and my colleague Shu Fan Wang for making this project possible overall. And to conclude, temporary encryption, I think, opens up new application, new use cases on blockchain that would not be possible otherwise. But of course, there are these drawbacks. It's difficult to implement properly and to develop. And we know that having faster finality and more compute, because we consume compute, could be relatively helpful. Now, I will link here the prototype that we built, which you can also find a link to the report. And that's it for me. I expect your questions.
So, amazing session, amazing bit of alpha there in privacy from Julie. So, questions are opening up to Julie now. Someone must have a question. I know we started a little bit slow today, but questions? I've got a question actually. So what's behind the curtain for the brand now? Like, where are you going with any announcements? Maybe something you can fill us in on.
So maybe you're not gonna like this, but there is no brand, there's nothing. I did my project, I got my ECTH credits and my master's, and now I'm working on something else. So it's out there for anyone to pick up. And if you have specific questions, more technical questions, of course you can ask me, and I'd be happy to contribute to anything that is built in this domain.
Amazing. It's always about sharing, guys. So please do find Julie after and come and talk about everything there. But thanks again. Once more, a round of applause for Julie, guys. So we have an exciting